Okay? So let p of x of 1 through x of n be a polynomial in the set of all polynomials in n variables with coefficients in the reals. Then the polynomial gives a function from n-dimensional real space into the reals. Notice in particular that n-dimensional real space is both an n-dimensional affine space and a topological space. Where the topology is the product topology. So in order to prove that a polynomial as a function from n-dimensional real space into the reals is continuous, we can use iterations of the previous corollary. And so this corollary is a corollary of the previous corollary. A function f from n-dimensional real space into the reals, a real-valued function, defined by a polynomial f of x of 1 through x of n in the set of all polynomials in n variables with coefficients in the reals is continuous. Okay, so proof. Notice that the function f is a sum over a finite number of indices alpha of functions f sub alpha, where f sub alpha is a constant multiple of the monomial x superscript alpha. So by part 1 of the previous corollary, the function f is continuous if each function f sub alpha is continuous. A sum of continuous functions is continuous. Okay, so now notice that each f sub alpha is a constant multiple of a function g sub alpha, where g sub alpha is the monomial x superscript alpha. So a constant multiple of a function is a constant multiple of a continuous function is continuous. So by part 4 of the previous corollary, each function f sub alpha is continuous if each function g sub alpha is continuous. All right, so we're going to continue to break down this polynomial. So notice that each function g sub alpha is a product of functions h sub 1 through h sub n, where h sub n, or h sub I rather, is the term of the monomial x sub I to the power of a sub I. So by part 3 of the previous corollary, each function g sub alpha is continuous if each function h sub I is continuous. Now, notice that each function h sub I is a finite product of the variable x sub I with itself So once again, by part 3 of the previous corollary, each function h sub I is continuous if the function p from the real line into itself, defined by p of x equals x, is continuous. So we have reduced a polynomial down to the identity function, and so it remains to show that the identity function from the reals into the reals is continuous, and once we prove this, that completes the proof. So choose a point x in the real line. We need to show that for every positive epsilon, there exists a positive delta, such that for every other point y in the real line, if the distance between x and y is less than delta, then this implies that the distance between p of x and p of y is less than epsilon. So let delta equal epsilon, and suppose that y is a real number such that the distance between x and y is less than delta. Then the distance between p of x and p of y is less than, or rather is equal to, the distance between x and y. Since we are dealing with the identity function, p of x is x and p of y is y, which is less than delta, which is equal to epsilon. And so the distance between p of x and p of y is less than epsilon. And so the function p is continuous at the point x. Now, as the point x was chosen arbitrarily, we have that the function p is continuous for every point in its domain, which is the real line. And so the function p is continuous. And so this cascades back all the way to our original polynomial. And so all polynomials, all real valued polynomials with real coefficients are continuous. Now, this theorem, or rather this corollary, can be amended to cover any n-dimensional affine space over a field F, as long as this field F is both an affine space and a topology. Or a topological space, rather. All right, so next we will begin to look at sequences and limits. Okay, so new definition. Let X be a topological space. A sequence in the space X is a function X mapping the positive integers into the space X. We denote the value of the function X at the integer n by subscript notation as X sub n, and the entire sequence is denoted as the set of those values. So let X sub n be a sequence in the topological space X. The sequence is said to converge to a point X in the space X, and it must be in the space, and this is denoted X sub n approaches X if and only if for every open neighborhood U of X there exists a positive integer m such that the elements of the sequence are in the set U for every value of n greater than or equal to m. That is, the open neighborhood contains all but finitely many values of the sequence. Alright, so now prove the theorem. Let X be a Hausdorff space. Then a sequence in the space converges to at most one point. So let's prove this. Let X be a Hausdorff space. And suppose the sequence x sub n converges to the point x in the space x. Now, as the space x is Hausdorff, for every distinct pair of elements, x and y, in the space, there exist open neighborhoods u of x and v of y, such that the intersection of those neighborhoods is empty. Now, as the sequence converges to the point x, there exists a positive integer, m, such that the elements in the sequence are in the set U for every value of n greater than or equal to m. That is, the set U contains x sub n for all but finitely many values of the integer n. Now, as U intersect V is empty, the set V cannot contain all but finitely many, cannot contain the elements of the sequence for all but finitely many, values of n. And so there exists at least one open set or open neighborhood v of y such that it is not true that there exists a positive integer, we'll call it p, such that the elements of the sequence are in the set V for every value of n greater than or equal to p. And so the sequence cannot converge to the point y in the space x. All right, so if we have a Hausdorff space, we are guaranteed a unique point of convergence if the sequence converges at all. And since we are assured, however, of a unique point of convergence, we have a special name for this. Let X be a Hausdorff space. If, let X be a Hausdorff space and let X sub n be a sequence in the space, if the sequence converges to the point X, we call that point X the limit of the sequence. And we write the limit as n approaches infinity of x sub n equals x, or more simply, the limit of the sequence x sub n is x, or equals x. All right, so we will end here for today. Next time we will continue to look at some important facts about sequences and limits, and then we'll move on to the quotient topology and quotient spaces. So I hope you have enjoyed the 19th lecture. Thanks for watching.